So, let us look at, well, I can quickly see that this particular constraint can be reduced to our standard set of natural boundary condition. Notice that in the special case, if we allow our sum of our variables to 0, let me call that there is no the point at 1 at the right hand side boundary is completely fixed, and also the y coordinate is not varying. So, which means that only the x coordinate on the left hand side is varying. In that case, my additional constraint reduces to x naught times the Hamiltonian, which is f minus y prime del y prime at x naught, and this is set equal to 0, right. So, this is the value that we set, and we see that this is nothing but our natural boundary condition if my end point at the left hand side for the x coordinate end point is not fixed. So, we recover our natural boundary condition in this special case. Okay. So, let me now discuss this general case a little bit more. So, in general, the general variable boundary point condition is going to satisfy the general endpoint condition satisfy constraints of the form which is non-holonomic. Constraints of the form this x naught g of x naught y naught x1 y1, well, x1 y1 is equal to 0, and this is in general a non-holonomic constraint, right, non-holonomic constraint, and often these constraints may reduce to a single endpoint constraints. So, what I am saying is often they these constraints could reduce could separate. We are going to look at this discussion with an example. This constraint separate to single endpoint constraints. Constraints to see that the constraints we get is gk of xj yj is equal to 0 if j is 0 comma 1. So, these are my single endpoint constraints, and example, well, the simplest example in this criteria is the fixed endpoint problem, right. So, for example, if I have fixed endpoints, problems, I can, let me say that xi comma yi is equal to is specified, right, is, so I from 0 and 1 is specified, right. The fixed endpoint problems xi yi's are specified. Okay. So, if the endpoint variations of x naught y naught are not linked to the endpoint variations of x1 y1. So, in general, well, these are the different cases I am trying to highlight. We will look at examples for each of these cases. So, in general, the endpoint variations, when I say endpoint variations, I am talking about delta x and delta y, right. The endpoint variations at x naught y naught are not related to the endpoint variations at x1 y1. So, in that case we will have set of two endpoint criteria which are completely independent of each other. So, in that case we have the condition p delta x minus h delta y, this is to be satisfied at x naught, and p delta x minus h delta y satisfied at x1, and these are two separate criteria. two separate criterias. Okay. Okay. So since if that is the case, since delta y and delta x, they are independent and arbitrary at each endpoint, we could certainly have that p and h, they are equal to 0 at each endpoint, right. So which means, okay, so let us look at some special cases of these criteria. So what I am trying to say is, let us look at some special case, special special cases, right. So special cases of the fact that, first case is we fix our x, right. We do not allow the x coordinate to vary, right. So in that case, my delta x is 0 and delta y is non-zero. So if that is the case, then my momentum defined at xi, which is del f del xi. Notice why we are taking the momentum, because p is the coefficient of delta x. So delta x is, so we have that, well, we have made a mistake here. This is going to be delta y, p delta y, right. Let us see whether we have the same condition or not. P delta y minus h delta x. So here is a small mistake here. This is h delta x. Okay. So in the first case, if delta x is 0, but delta y is not 0, but the linear combination is 0, that is only possible when the coefficient of delta y is 0. So if delta y is not 0, then the coefficient, which is p of xi, the derivative of f at the primed value at xi is 0, right. So these are, so this is for I equal to 0 and 1. So these are my natural boundary condition, right, natural boundary condition. Similarly, if we can fix my variable y, I see that delta x is not 0, and of course variable y is fixed, so delta y is 0. If delta x is not 0, which means that the coefficient of delta x, which is h of xi, which is going to be y prime p minus f evaluated at xi, this is set equal to 0 at the endpoints I equal to 0 and 1, right. Okay. So we are going to see that although we have completely described these variable endpoint functionals, the extremal of these variable endpoint functionals, but in many cases the endpoint criteria pose severe restriction on the extremal that is generated as a solution to the Euler-Lagrange equation. So what I just said is that our endpoint criteria that we have found, endpoint conditions, they pose additional, sometimes very limiting restrictions, additional restrictions on y, generally incompatible with my Euler-Lagrange equations, right. So generally pose additional restrictions on y, generally incompatible with Euler-Lagrange equations. So let me look at an example, right. So suppose j of y is equal to integral from x naught to x1 f of x comma y prime dx, right, where my f does not depend on x explicitly, right, where I am looking at a specific class of functional. I allow my f such that f does not depend on x explicitly, and students are familiar that the optimization of this class of functional will lead to the Beltrami identity, setting that identity equal to a constant. So which means let me call this relation as A. Using the Beltrami identity, I get that h, which is y prime p minus f is equal to a constant. So, that is the reduced Euler-Lagrange equation. Now, also our endpoint criteria says that we have a fixed x, right. So, we have, suppose we also impose that we have a fixed y. So, what have we got is, so for the case if we have fixed y, we have fixed y at the endpoints, that is delta y is 0. So, fixed y at the endpoints or delta y is 0, then this leads to our reduced bound endpoint condition that h at xi is 0. So, I get the endpoint condition to be the Beltrami function h of xi equal to 0. So, which means from A and B I see that the solution to the Euler-Lagrange is such that the Beltrami function is identically equal to 0 for all xy, right, because it is 0 at 1 x or at 2 at x, which is at x0 and x1. So, it must be 0 for all x, right. So, which means from my Euler-Lagrange and from my endpoint criteria I see that h is identically 0 for all x in the interval x0 to x1, right. So, or I see that the Euler-Lagrange equation reduces to partial f partial y prime is equal to f, right. From here I see that my f of y comma y prime is equal to, if I integrate this relation, I see that this is equal to a y times y prime, which means that this class of functional with variable endpoints such that the y coordinate is fixed can only be solved if the integrand of this functional is linear in y prime, right. So, we could only get a solution for this fixed form of f, otherwise we will not get the solution, right. So, let us look at a proper example in this discussion. So, we want to extremize our functional j of y, which is integral 0 to x1 1 plus y prime square dx. We want to extremize this such that one of the endpoint is fixed and the other endpoint is also fixed such that its y coordinate is fixed, but x coordinate is not. We do not know x1. So, x1 is unspecified, right, x1 is unspecified, and again we see that this function is independent of x. So, we to find the extremal we can right away use the Beltrami identity. Okay. So, which means that that my Beltrami function h of y comma y prime, which is y prime partial f partial y prime minus f, must be a constant, right. Now, we plug f is 1 plus y prime square. I see that this is going to give me y prime times 2 y prime minus f, which is 1 plus y prime square, which is also equal to y prime square minus 1, this is also equal to a constant. So, that is my reduced Euler-Lagrange equation, but also note that since my delta y is 0, but delta x is not 0, that is the variation of the boundary point are such that only the x component is varied, but y is fixed, which means our endpoint criteria gives us that the Beltrami function or the Hamiltonian at xi is 0, right. From these two criteria, from these two conclusions, I can say that so this is at xi at x0 and x1, right. from these two conclusions I can conclude that the joint conclusion is that the Beltrami function y prime square minus 1 is identically equal to 0 for all x y, right. No, for all x in the interval x naught to x 1, okay, which is 0 to x 1. Okay. So, then all I have to do is to solve this equation that I have found. I see that y prime square is equal to 1 or y prime is equal to plus minus 1, right. Now we are we have to, it seems that we have two solutions, but note the boundary conditions. So, we have that y of 0 is 1 and y of x 1 is L, which is greater than 1. So, which means y is increasing, it is increasing in the interval 0 to x 1, right. So, which means that we take the solution y prime is equal to 1, that is the derivative must be positive for the solution to increase, or from here I get that y is x plus a constant c and also y of 0 is equal to 1. So, this c is 1 and hence I get my extremal. Okay. So, then let us look at an example of this variable endpoint problem with functions with integrands of the functionals containing multiple dependent variables. So, functions with several dependent variables, I see that I can write my functional j of q is equal to integral from t0 to t1 L of t comma q bar dot dt, right, where my q bar is q1 to qn. Okay. So, what have we got? We have seen that j is stationary, at q if first of all the Euler-Lagrange, the system of Euler-Lagrange equations are satisfied. If I have this following ODE being satisfied, del L del q k dot minus partial L partial q k, well, so this is L is equal to 0 for k equal to 1 to n, right, and for variable endpoints we must have that the summation, the variable endpoint condition summation p k delta q k minus h delta t. So, t is my independent variable. So, h delta t is 0 for k from 1 to n. So, that is my at endpoints x0 and x1, at endpoints x0 and x1 or in terms of free variable independent variables t0 and t1. Okay. Let us now look at an example in this class of functionals. The example that I have is as follows. We want to extremize this integral from 0 to 1 of q1 dot square plus q2 dot, well, q2 dot minus 1 whole square plus q1 square plus q1 q2 times dt for the boundary condition q at 0 is q0. So, we have fixed one endpoint, but q at 1 is free. So, we have fixed the x coordinate of the boundary points, but we have kept the y coordinate, one of the y coordinate to be variable. Okay. So, again we impose the Euler-Lagrange constraint. My Euler-Lagrange equation for this system of the system of Euler-Lagrange equation is as follows. I get two Euler-Lagrange equations, minus q1 minus q2 is equal to 0, and So, this is for first component, and for the second component I get 2 q2 dot minus q1, this is also equal to 0, and from here I see that I get 4 q2 to the power 4. So, what I am trying to do is to solve, I first eliminate one of the variables by taking the second derivative of the second equation and eliminating q1. I get that this is 4 q2 double dot minus q2 is equal to 0, right. And from here I get a set of solutions. The solutions are q2 of t is equal to c1. So, we get a linear combination of exponential solution, right, as well as sine and cos solutions, plus c2. Let me write this entire expression, sinh of at plus c3 cos of bt plus c4 sine of bt, right, where a and b are these constants, square root 2 plus minus 1 by 2 to the power 1/2, right. Now, there is no variation in the free variable t, since t0 is 0 and t1 is 1, it implies my delta t is 0, no variation in the free variable, right. But so which means my end point, so this statement is implying that my end point criteria, my end point condition reduces to pk delta qk is equal to 0, right, for k equal to 1 and 2. So, from here all I have to do is substitute the value of qk, because delta qk is non-zero. So, this is equivalent to saying that pk is equal to 0, right. So, what is pk? Pk is partial L partial qk dot. So, this partial derivative is set equal to 0 for k equal to 1 and 2. From here these are the two conditions I get. From here I get two equations satisfying at the boundary. So, this is at t equal to 1, at the other boundary which is variable, right. The first boundary is fixed. So, at the variable boundary condition we need to differentiate, we get the two conditions, we differentiate L is this quantity. So, partial L partial q1 dot is 2 q1 dot at t equal to 1 set equal to 0, and the second one is 2 times q2 dot minus 1, this is at t equal to 1 set equal to 0, right. So, these are my two conditions, and now I am left. So, notice that my q2, from here I can always find q1 of t, but note I have from here in this description I have 4 constants c1, c2, c3 and c4, but I have 2 endpoint condition and I also have 2 boundary condition which will fully determine these constants which are 4 unknowns of the problem. So, I am not going to mention the value of these CIs and leave the problem for the students to find out the value of these constants in terms of q naught bar here, this one, okay.